Good day, everyone. In this presentation, I will discuss the remaining key concepts related to the Carnot cycle. Understanding these ideas is important because the Carnot cycle represents the theoretical limits of efficiency for any heat engine. So now let's proceed to the Carnot cycle and the second law of thermodynamics. So the Carnot cycle is directly connected to the second law of thermodynamics. This law states that no heat engine can be more efficient than a Carnot engine operating between the same two temperatures. So in other words, the Carnot cycle defines the maximum possible efficiency that any heat engine can achieve. So the second law also emphasizes that some energy will always be lost as waste heat. Because of this, 100% efficiency is impossible. So here's a diagram that shows why a super efficient engine cannot exist. So here's on the orange side, we imagine a super efficient engine that produces more work and rejects less heat than a Carnot engine. So in the blue section, this engine is connected to a Carnot refrigerator which uses the extra work to pull heat from the cold reservoir and push it back into the hot reservoir. So when they work together, the system ends up converting all the heat from the hot reservoir into work, with no heat released to the cold reservoir. So on the yellow side, the diagram shows that this combination behaves like a 100% efficient engine, which is impossible because every real engine must always waste some heat. So this proves a super efficient engine cannot exist. And the last one is the Kelvin temperature scale. To properly evaluate the efficiency of a Carnot engine, we use the Kelvin scale, the absolute temperature scale in thermodynamics. The Kelvin scale starts at absolute zero, the lowest possible temperature where particle motion theoretically stops. Unlike Celsius, Kelvin has no negative values.
Here's an example problem. An inventor claims he has designed an air-cooled gasoline engine made entirely of copper that achieves 85% efficiency. Should you invest in this engine? So here the efficiency can be no better than that of a Carnot engine running between the same two temperature limits. And Carnot equals 1 minus T sub C over T sub H. So the temperature of a cold reservoir for this air-cooled engine is about 300 K or the ambient temperature. And the temperature T sub H of the hot reservoir cannot exceed the melting point of copper, 1356 Kelvin. Hence, the maximum possible Carnot efficiency is N equals 1 minus 300 K over 1356 Kelvin equals 0.78 or 78%. Thus, the temperature of any real engine would be less than this, so it would be impossible for the inventor's engine to attain 85% efficiency.